we are supposed to let a liquid jet fall onto a surface, and when we illuminate the contact point with a laser beam, we can observe the formation of rings of light around the jet, as you can see in the picture over here. And so our task for this problem is to investigate these light rings and determine how they depend on the relevant parameters of the system. So for this, here are the contents of my presentation. So I'll start off by explaining how we constructed our experimental setup and some of our key preliminary observations. Afterwards, I'll formulate a qualitative account to explain the formation mechanism of the light rings. And afterwards, I'll proceed to develop a quantitative theory and use it to predict the location and intensity of the light rings. And these will be then verified experimentally using our experimental setup. So first, our experimental setup. To create our water jet and create a constant jet pressure, we use an overflowing water tank, as you can see over here. And this water tank is actually connected to a vertical tube, and this tube is placed over our horizontal white tile. To illuminate our jet, we use a monochromatic unpolarized laser, and this is placed at an angle elevated using a retort stand. To record images of the phenomenon, we use a DSLR camera, which is tripod mounted, so that we can change its location easily. And we also have a side camera, which is placed level to the water flow, and this allows us to capture images of the flow profiles. So here are some of our preliminary observations. First, we know that in our experiments, we are able to consistently obtain the formation of two bright rings, as you can see, as well as a ring at the base of the water jet, as shown here. Secondly, we are able to observe the formation of dimmer secondary rings between the primary rings, as you can see bracketed over here in the picture. And third, we are able to observe the formation of multiple rings when we observe the setup from higher elevation angles, as can be seen in this picture. Finally, that's not so sweet sound. Finally, when we replace the white tile using with a mirror, we do not observe the formation of the light rings, as you can see in this video. And we note that diffuse reflections are necessary for the formation of the light rings. So now with this, I'll proceed on to a qualitative account of the phenomenon. So here's a preliminary model of our system, in which we have a water jet which impinges upon a white tile, and we also have a laser and observer. So when the laser beam first hits the tile surface, there will be diffuse scattering of the light due to the white tile, and these light rays will then take various paths out of the system, and some of it will eventually reach the observer. We can then intersect these light rays with the water flow to obtain the position of the perceived light rings. So in order to do so, we will be coding a preliminary simulation using ray optics, and we'll be using the following equations, Snell's law as well as the law of reflection in vector form. So our simulation works as follows. We first designate a point at the bottom of the white tile as a laser spot, and then we send an array of rays from the observer to the water flow, and we simulate its path through the system for a few iterations. Finally, we then check which of these rays land on the laser spot, and we select them. As you can see, these green rays are the ones that eventually hit the laser spot. So using the principle of reversibility of light, if diffuse light is emitted from this laser spot, these light rays will actually follow the green paths to reach the observer, and then we can use these light rays to intersect with the water flow to obtain the predicted positions of the light rings. So we ran two versions, one considering the effect of partial reflections and one without, so that we can clearly observe its effects. So here are some of our simulation results, where the solid surface represents the surface of our water flow, and the blue dots represent the positions of the light rays which reach the observer. So as you can see, the light rays are predicted to be observed from all camera angles which are consistent with our observations. This is also a set of simulation results for changing the radius of the laser beam. And as you can see, as we increase the width of the laser beam, the light rings become thicker and thicker until they eventually merge together to form a continuous band of light, as can be seen in the picture on the far right. So with these simulation results, we conduct some preliminary experiments, and we can overlay our theory and experiment graphically to obtain the following overlays. We can see that the position of the primary rings has been quite accurately predicted by our preliminary simulation. Here is another set of data for a different camera angle, and we see that the positions of the primary rings has been predicted rather well. However, there are some flaws with our preliminary simulation. First, we note that especially for the simulation with the partial reflections, our simulation does over-predict the number of rings that are formed, and quite a number of these predicted rings are actually not observed in our experiment. And we note that this is due to the fact that these rings are actually too dim to be observed, as they are formed by repeated partial reflections of the water flow. However, a more important point is that our simulation does not actually predict the existence of the secondary rings. As you can see in this comparison, the secondary rings which are boxed up in white do not show up in our simulation in the positions which they are supposed to show up in, which are boxed up in red. So to understand why this is the case, we go back to our simulation and we note that our simulation actually does not consider the effect of secondary diffuse reflections. So what is this effect? I'll go on to elaborate. So first, when we note that when our laser beam hits the white tile, we can designate an area on the white tile which we can define as a primary laser spot. So in this naive model, this would be the only source of diffuse light. However, we must note that when light reflects diffusely off this surface, some of it will reflect partially off the water flow and impinge the tile surface again, forming a very large effective laser spot. Then after this, more diffuse light will be emitted from this effective laser spot, and some of this will eventually reach the observer too as well. So we hypothesize that this could be the cause of the secondary rings, and in order to verify if this is the case, we proceed to come up with an experiment to deduce this. So on the left, we have our typical experimental setup, which involves the use of a white tile as our surface. And on our right is our modified experimental setup for this purpose, in which we have a large piece of mirror with a small circular disc of blue tack placed at the center, and this blue tack has dimensions of roughly our laser diameter. The effect of this setup is to mimic the lack of higher order diffuse reflections in our simulation, because the area of diffuse reflection is limited to the size of the blue tack itself, which is modeled to be around the size of the laser beam. So if our hypothesis is correct, if we use the second setup to obtain the light rings phenomena instead of our usual setup, we will not be able to observe the formation of the secondary rings. So we put this to the test experimentally, and here are the images of our typical and modified experimental setup with the ambient lighting, and we can clearly see the piece of blue tack over here which we place on our mirror. So we switch off, we take away the ambient lighting, and we can ignore these rings below because they're caused by reflection of the mirror. So we note that the secondary rings which we typically observe in our normal experimental setup are actually absent in our modified setup, and indeed there are no secondary rings formed. So this actually verifies our hypothesis, and the secondary rings are indeed caused by the mechanism of secondary diffuse reflections. So now that we have completely understood why these secondary rings are formed, we can move on to further investigate the formation of the primary rings, and we do so using by changing the size of the laser spot. So for this segment, we use a permanent marker instead of a laser beam, and this is valid because the permanent marker spots can also act as sources of diffuse lights. So for this, we drew dots of different sizes on our white tile, and we observe the image of the dots through the water flow, and using this, we can observe some interesting effects. So here are some of the images we obtained for a decrease, various dot sizes in decreasing order. So we note that for larger dots, we observe what we usually do with the laser beam, which is the formation of two rings of light. However, if the spot is too small, we only observe one ring of light, and this ring is also not a complete ring, as you can see. So to understand this, we go back to our model, and we see that the first primary ring is caused by direct transmittance through the water surface, as can be seen in this illustration. And the second primary ring is caused by a single internal reflection of the water surface. We note that for a significant amount of light to be reflected off this water flow, the incidence angle between the light ray and the normal of the water surface must be very large. And for this to happen, the second primary ring, for the second primary ring to be observable, the spot must be large such that there's diffuse light emitting, which allows the large incidence angle to be formed. And this is why we do not observe these secondary rings when the laser spot is too small. So we can extend this investigation and observe the other case where the laser spot is very big. And we see that the rings are no longer discrete and instead form a continuous band of light. And we know that this is also corroborated by our preliminary simulation earlier on. So we can use these results to draw some interesting conclusions about the light rings. So we see that in our experimental setup, our laser spot is actually very small. However, the effective laser spot caused by the higher order diffuse reflections is actually very large, over a few times the diameter of the water flow. And because of this, and from our freeze-based results, we see that when the laser spot is large, what we get is a continuous band of light rather than discrete light rings. So from this, we can conclude that the light rings that we observe typically are not discrete as what we would normally intuitively expect. However, they are observable, they are merely peaks in the continuous intensity distribution along the height of the water jet. So with this, we can summarize our qualitative theory as such. When the laser lands on the white tile, there will be diffuse reflection, and this will cause light to be reflected off the water flow and into the observer, and these will form the primary rings. At the same time, due to the partial reflection of the water flow, there will be an effective laser spot that is formed, and this will lead to further reflection of the water flow, which will eventually form the secondary rings. So now that we have a full, better understanding of the phenomenon, we shall proceed to model the entire phenomenon accurately numerically. So we split this into two parts. The first part is to model the water flow itself, and for this segment, we'll be using the incompressible Navier-Stokes equation, which is essentially the Newton's second law applied in fluid dynamics. So the box terms represent the inertia, the pressure gradient, the viscosity, and the volume force in the liquid. And we know that our incompressibility approximation is indeed valid because the number is much less than 1. The volume force term can actually be written in terms of the gravity force as well as the surface tension, and we'll be using the surface normals to calculate this surface tension of our liquid. Afterwards, we apply the continuity equation, which basically implies the conservation of mass, as well as the boundary conditions, which is the no-slip boundary condition along the wetted surfaces, and we can then simulate for the movement of the fluid in our system. So here's an example of simulated water flow in 2D and 3D. We can indeed verify that this matches our experiment well by overlaying our theory versus experiment, and we will be using these simulated water flows for our ray tracing segment. So for the second part, which is the optics part of the formula, we'll be using ray tracing once again. However, we'll be tracing from the laser instead. So first, we send out a ray of laser from the laser source, and we'll be applying the law of refraction at the liquid interface to obtain the geometry of the illuminated region. We note that we can approximate the intensity of our laser to follow a Gaussian distribution shown by this graph. We can then apply the Fresnel equations to obtain the intensity of the illuminated region. And here is a sample of the theory, and we can see that there is some slight distortion when the laser beam passes through the water flow. Next, once the laser hit, we simulate the laser hitting the spot. We can simulate the diffuse reflection at the tile surface by using a Lambert diffuse intensity profile with a specular component, which is what we need for our white tile. The coefficients of this intensity are characterized in a separate experiment with the following coefficients. We note that the higher order diffuse reflections are too computationally intensive for us to account for because of the nonlinear nature of the ray tracing. Hence, we will not be considering this effect in our simulation. So finally, after we emit the diffuse rays, we then simulate the path of these rays through our system, and we then eventually solve for the rays that intersect our eye. And these will form the images of the light rings that we observe. So here's some of the sample plots for our ray tracing program, and you can see the light rings in red at the bottom right corner. So with our numerical model, we proceed to experimentally verify this. So here's firstly a plot of the eye position against the viewing angle, which is denoted by theta I in the diagram over here. And here's our experimental data. We see that there's a very good agreement which shows that our numerical simulation is indeed accurate. And at the same time, we also observe a very clear increasing trend. And to understand this, we can understand this in terms of the path of the light rays in our water jet. So we see that as the elevation angle increases, the angle of the light rays needed such that they eventually intersect our eye will also increase. And due to this increased angle of the light rays, they will travel a larger height in our water flow, which leads to the increased height in the observed light rings. Next, we have a plot of the ring height versus the flow velocity of our water flow for 4mm radius pipe as well as a 6mm radius pipe. And once again, we see good agreement between theory and experiment. We also observe a very clear increasing trend, and to understand this, we can think about the angle, the light rays in our water jet once again. So we see that with a larger flow velocity, the necking effect in our water flow actually decreases, and at the bottom of the water jet, it becomes thicker. Due to this increased thickness with increased flow rate, we see that the light rays will actually have to travel a further distance in our water flow, and this also once again lead to an increase in the ring height. So with investigations, with this we can also move on to investigate the effects of ring intensity. And so we note that from our previous observations, the third primary ring is very hard to observe in most of the elevation angles. In our simulation, is actually able to show this as well. So we see that the first and second primary ring have observable intensity, however the third primary ring is actually too dim to be observed, and it's actually 10 to the 4 times lower than the first primary ring. However, if we increase the observation angle, the third primary ring increases in intensity and hence it becomes observable during our experimentation. So here is a summarized plot of the effects of the viewing angle against the intensity of the light rings, and we see a decent fit between our theory and experiment. We see that the perceived bright rings, the perceived brightness of the rings increase as we increase the viewing angle. However, and we also see that the third primary ring is too dim to be seen for most of the viewing angles because of the visibility threshold, which basically means that we are unable to detect very negligible amounts of intensity. However, we also note that near the 90 degrees observation angle, the intensity of all three light rings actually decrease, and this is due to the fact that the partial reflection has a much greater role here, and this will decrease the intensity of all three light rings. So, in conclusion, for the problem, I managed to experimentally replicate the light rings phenomena with our experimental setup, and I've also managed to account for the formation of both our primary rings and secondary rings qualitatively, and these mechanisms have been verified experimentally. And from this, I've also managed to deduce the non-discrete nature of the light rings from our findings. In determining how the light rings depend on the relevant parameters, I coded a ray optics simulation considering the diffuse reflection, and also managed to model the geometry of our water flow, and I investigated how the ring height and intensity depend on the eye position as well as the flow rate, and I managed to obtain decent agreement between our theory and experiment. So thank you very much. Yeah, so I guess I wasn't very fluent, but that's the gist of my presentation. So if you have any questions, either relating to this or just the SYPT or IYPT in general, just feel free to ask. So does anyone have any questions?
You can raise your hand, we can pass the mic to you. Anyone have any questions? About SYPT? So maybe I'll ask them. So Wittmann, how do you, what are the challenges when you are doing this experiment? Could you share some of the challenges?
Okay, right. So basically, I'll go back to my presentation. Hold on. Okay, basically, one problem we face in our this problem is actually the explanation for the secondary rings itself. So basically, for the simulation part, because we use the first simulation we coded actually uses this method where we send the rays from the eye instead of the laser, because this actually is a lot less computationally intensive. So with this simulation, we actually couldn't really replicate. We are able to obtain the positions of the primary rings. However, there was when we tried to fit our theory to our experiment graphically, as we showed you just now, we were not able to reproduce the secondary rings, and this really stumped us for